How do intelligent agents move from an idea to a working system? This topic covers how agents perceive, reason, act, and improve within their environment. You will follow the main design steps, implementation tools, market applications, and ways to evaluate performance in competitive settings. Designing and implementing intelligent agents means creating autonomous systems that can perceive their environment, reason about what they detect, and act to achieve specific goals. A structured approach matters. It connects theory, tools, coding models, simulated environments, reasoning strategies, and evaluation into one practical workflow: 0, 2, 0, 3, 0, 4, 0, 5. The design process starts with problem definition, then moves through architecture design, perception, reasoning, action, and communication. Each part supports the next. This structure helps you define what the agent should do, how it will decide, and how it will interact with users, systems, or other agents. Problem definition begins by identifying objectives, understanding constraints, and specifying goals. Objectives state what the agent is expected to solve. Constraints include environmental, computational, and operational limits. Goals should be measurable and achievable, so later design choices can be tested against clear expectations. Agent architecture defines how an agent perceives, reasons, and acts. Reactive architecture focuses on stimulus response and suits real-time systems, such as robotic vacuum cleaners. Deliberative architecture uses symbolic reasoning and planning. Like route planning in global positioning systems, hybrid and learning architectures extend these ideas for more complex behavior. Perception starts with sensors such as cameras, microphones, global positioning system sensors, or other inputs. Pre-processing filters raw data, such as converting audio signals to text. Reasoning may use rule-based systems, search algorithms, or reinforcement learning. Action modules then use actuators, application programming interfaces, and action planning to execute decisions. Communication modules support both internal and external interaction. Internal communication in multi-agent systems may use protocols such as Foundation for Intelligent Physical Agents, compliant messaging, while external communication may use representational state transfer application programming interfaces. Testing then checks performance, scalability, robustness, and adaptability, while implementation must handle complexity, uncertainty, coordination, and safety concerns. Python is popular for artificial intelligence and machine learning libraries. Java is known for scalability and integration with agent platforms, while C++ offers high performance. Java Agent Development Framework supports multi-agent systems. NetLogo supports simulation, and TensorFlow, PyTorch, Robot Operating System, and OpenAI Gym extend learning and robotics work. One design example is an autonomous delivery drone for urban package delivery. The problem is to deliver within a city while avoiding obstacles and optimizing delivery time. The design uses a hybrid architecture with reactive obstacle avoidance and deliberative route planning, showing how the earlier steps combine in one applied system. In this drone example, perception uses global positioning system for location and LiDAR for obstacle detection, with filtering for noisy sensor data. Reasoning combines reactive rules for immediate avoidance with a star search for route optimization. The action module uses motors and a delivery arm, while communication coordinates fleet drones and notifies users. Structured models help agents interact, process information, and achieve goals in code. This starts with selecting an architecture and defining communication mechanisms. The material highlights layered, modular, and blackboard-based architectures, each offering a different way to organize perception, reasoning, action, and coordination in intelligent systems. Layered architectures organize functionality into perception, reasoning, and action layers, with reactive, deliberative, and learning layers as examples. Modular architectures separate independent functions such as navigation, communication, and task execution. Blackboard-based architectures let agents or modules read from and write to a shared data structure for collaborative coordination. Multi-agent communication can use direct message passing through predefined interfaces or more formal foundation for intelligent physical agents, compliant messaging with performatives such as request, inform, or propose. Compared across complexity, adaptability, communication style, and use case, layered models are moderate, while modular and Blackboard models suit more complex collaborative systems. Python is presented as a practical language for programming agents because of its intuitive syntax, library ecosystem, and integration with artificial intelligence, machine learning, and robotics frameworks. Libraries named here include Mesa, Aromas, and PyDatalog. Python also supports simple reactive agent implementations and broader agent-based systems development. Design patterns improve modularity, scalability, and maintainability. The observer pattern lets agents react to state changes in the environment or other agents. The factory pattern supports flexible agent creation. The singleton pattern fits shared components such as a blackboard, and the state pattern lets agents change behavior based on internal state. Reliable agents need testing and debugging. Unit testing checks individual components, such as perception, reasoning, or action modules. Integration testing checks component interactions and communication protocols. Simulation testing uses tools such as Mesa or Pygame. Debugging methods include logging, visualization with Matplotlib, and breakpoints in integrated development environments such as PyCharm or Visual Studio Code. Simulated trading environments provide a controlled way to test and evaluate trading agents. They reproduce market dynamics so agents can compete, adapt, and refine strategies under realistic conditions. The main themes are agent competitions, market dynamics, and programming trading strategies in Python for buying, selling, or holding assets. In trading competitions, multiple agents participate in a simulated marketplace to maximize profits. Performance can be judged through profit, risk management, and strategy efficiency. Agents must also handle price volatility, market events, and liquidity or volume changes. Real-time reactions to prices and signals are central to competitive behavior. Trading strategies can range from simple heuristics to advanced learning models. One example is the simple moving average strategy, where an agent buys when a short-term average rises above a long-term average and sells when it falls below. Another example is reinforcement learning using OpenAI Gym and stable baselines. Practical reasoning helps agents make decisions, adapt to market dynamics, and optimize outcomes in auctions, trading platforms, and resource allocation systems. The material focuses on decision-making algorithms and learning from interactions. Agents choose actions based on available information, market conditions, and their own goals in competitive environments. Auction strategies include utility maximization in first price auctions, truthful bidding in second price auctions, weighting in Dutch auctions, and incremental bidding in English auctions. Market decision methods include reinforcement learning, utility-based decision-making, and game-theoretic approaches. Learning can come from Q-learning, deep reinforcement learning, evolutionary algorithms, or imitation learning. Evaluation in competitive settings uses economic, strategic, behavioral, and robustness metrics. Examples include profit maximization, cost efficiency, win rate, Nash equilibrium compliance, adaptability, collusion avoidance, performance under stress, and failure tolerance. Testing methods include simulated environments, competitive benchmarks, stress testing, and multi-agent interactions, alongside awareness of overfitting, scalability, and ethical concerns. Together, these elements support the development of robust and adaptable agent-based systems.